Yeah, I'm going to be talking about some work I've been doing recently on quantum error correction. Um, I'm coming from a condensed matter physics background, and that's going to be part of the motivation for this talk is also going to be coming from that. But in these works I've been trying to do something that is also useful for quantum error correction. So that's what I'm going to be telling you about today. The talk today is going to be about this question, which locally interacting many body systems have dynamics that stabilizes quantum information. Okay, so I want to know what many body systems, by virtue of their natural native dynamics, protect quantum information for a long time. Okay. So this is what I'm thinking of. We have some locally interacting quantum system here. It's coupled to a bath. The evil face on the bath is to note that the bath may be of arbitrary character. It may interact with the many body system in an adversarial way. But what we want to design is we want to design the dynamics of the system in such a way that as long as this coupling is weak, then no matter what the bath looks like, this system can retain quantum information for a long time. Okay. So that's the goal. Maybe I'll try to move else. Now, why might you be interested in thinking about this question? Well, there are a couple of reasons. The motivation that was motivating me when I set out to do this type of work was classifying quantum phases of matter which are stable against perturbations. So something that I find really interesting is the kind of classification of different types of phases of matter. That's a question that is just beginning to be addressed in the context of open quantum systems. So a lot of condensed matter people right now are thinking about this question. But we're pretty far from having a general picture of what these things look like. Another reason might be that you want to do quantum error correction very quickly. So if you have a quantum many-body system and the dynamics that it naturally runs stabilizes quantum information, then you don't need to send everything out to a decoder to do to stabilize the quantum information, and things can be done much more quickly. Okay, so I'll talk about this more in a second. So today we're going to be talking about this question in the context of the surface code. Really, any abelian topological code will do, though. So this is the one slide where I figured for this audience I wouldn't really go into detail about the exact details of the surface code. We have a surface, we have anyons, and what we're trying to do is we're trying to make sure that pairs of anyons don't go around the system without us noticing. Right? That's the error correction task we're faced with. So I just wanted to briefly kind of sketch how error correction in the surface code is currently done. What happens is you store a space-time history of all the syndrome measurements that are made during the experiment. You collect all of that data, you send it to a classical CPU, which is sitting outside of the quantum device. You run some particular error correction algorithm on the accumulated data, and then you use the result of that algorithm to perform feedback on the quantum device and correct the errors. Right? Okay. So this is what it looks like in one particular example, right? You have the surface code is sitting somewhere inside the dill fridge, and then you have all this cake wiring to transmit all the information back to a classical computer, which is doing error correction, among other things. Right. Okay, so this is the setup, but this approach has a few drawbacks, and among those are the following. So one is there's some latency. So superconducting processors in particular are very fast, and they could get even faster. And in regimes where computations and error correction need to be done very quickly, this latency of transmitting all the information outside of the device can actually be non-trivial. Then you also have the problems of heating and the kind of engineering demands that you get when you have to poke your dill fridge with a million different holes, one hole for each qubit, right? And adding like separate little control lines to read off every single stabilizer in your quantum memory is not really scalable, right? So if we're going to really take the superconducting processor approach seriously and do useful computations with it in the future, we're going to have to reduce these problems, mitigate these engineering challenges.
It's like 3 holes per qubit.
Yeah, so we definitely don't want that, right? So we need to be able to control the qubits and do information processing. So we might need, say, 3 holes per logical qubit, but 3 holes per physical qubit seems pretty bad. So there are ways of doing, gates and reading out measurements which don't need to poke the hole in the entire fridge and can confine everything into a lower temperature environment. But what still needs to be done is to figure out how to take the whole error correction stack and put that in the fridge as well, right? So that's the bottleneck. So kind of just said this, but what may be required in the future is that we may need to put the whole error correction stack inside of the fridge. Okay, so we get rid of this whole poking issue, right? I'm not going to commit in this talk to where exactly it's going to go inside the fridge, but suffice it to say, it's going to have to go in there somewhere. And since dill fridges just don't get rid of heat very well, you're not going to be able to just put an entire CPU inside of the dill fridge, right? So if we're going to design a quantum error correction algorithms which work in this setting, they're going to have to be very lightweight, right? And by lightweight, I mean they're going to have to be very fast. Of course, they're going to have to be accurate, but they'll also have to be very simple because running minimal weight matching through a CPU just generates too much heat. Okay. So there's a lot of work that's been done on developing the kind of classical hardware and control infrastructure that would be needed to make something like this work. Some of the references are listed on the bottom of the screen if you're curious. Okay. So with this in mind, the kind of ideal quantum error correction solution that one would imagine is something that looks like this. So you would have your qubits laid out in a grid, and at the location of each stabilizer where you're measuring the system, you would place a tiny processor, ideally with like a constant number of bits of RAM. And these processors would interact with the system. They would locally measure the system, exchange information with their neighbors, and through this collective network of processors, hopefully perform error correction. So this is like Jim's idea back in the early 2000s, and I think this question is becoming even more relevant in modern era. And if we can arrange an autonomous network of processors which perform error correction, then we can basically do error correction arbitrarily fast. Okay. So if these guys operate in real time, there's no speed limit on error correction. Okay. And additionally, if these are very simple, then we also are not dissipating really any heat. Okay, so these are called cellular automaton decoders, and I'm just going to give a very brief couple slide overview of what is known about doing error correction in this way, right? So the first way, the original way due to Jim, is using a procedure that's roughly akin to doing block spin renormalization group, but on anyons. So you design the feedback rules of these processors in such a way that they kind of like mimic a renormalization group flow on the pattern of anyons in your system. So Harrington's decoder, this was the original proposal. Then with Margarita and Shankar, I kind of came up with an alternate way of doing this. The differences there are maybe a bit technical. I'm not going to go into. But okay, suffice it to say, there are these existing approaches. The problems with these approaches is that the dynamics that is used is very inhomogeneous in space-time. So the gates that are applied to your system are arranged according to this very elaborate hierarchical pattern, which is not it's not something that's going to be implementable by like a local Lindbladian, which is, as a condensed matter person, what I ultimately want to be there for doing error correction. Another problem empirically is just that the thresholds are pretty small. So these are numerics done by different authors on Harrington's decoder. I think for various reasons that you'll see in the rest of the talk, I'm not sure how confident we can be that these indicate a threshold. And then the thing with Shankar and Margarita is much worse, actually. So forget about using that for anything practical. Yeah, and a problem with these is that they're only defined on system sizes, which are power of an integer. So they're not really very amenable to experimental or theoretical study. Okay. A more physical approach, which I really like, and which was the motivation for the work today, is the following. The idea is very simple. You use this network of processors to induce an effective attractive interactions between anyons. So you use the processors to simulate like a gravitational field that the anyons possess, and you hope that by moving the anyons around according to this gravitational potential, they will just sort of naturally pair themselves up, and your errors will take care of themselves. Okay, so you want to have the processor simulate a field like this, and then move the anyons along the gradient of the field. Okay, does that make sense?
How seriously should we take that analogy? Is it because you're gonna have orbits and this?
Orbit, that would be cool. We don't. I'll tell you the exact kind of gravity we are. Of course, gravity in 2 dimensions is not going to really work because it's you don't have actually propagating degrees of like it's not. We don't have a graviton. There's not a express tensor and everything. But it just means that well, I say gravity because I just mean that all of the anyons are attracted to every other anyon.
Right. But
Yeah.
What's the kinetic energy term?
You'll see in right now. Okay, so the best candidates in this direction were written down in these papers from a little less than 10 years ago. And how this is exactly what they do. So they take each processor to store a single real number, basically, which is a scalar field. And they take it to be updated according to this equation. This is a Poisson equation, and it's sourced by the anyons. So it's very simple. The anyons, by exchanging this field, they just behave like attractive. They are subject to an attractive power law interaction.
So it's quite close. I guess the dynamics of the anyons you haven't specified.
I haven't specified, but this is this
Oh,
you just move them along the gradient of the potential.
So they don't have their own kinetic energy.
No, they just do whatever the field is telling
Oh,
them
I
to do.
see. Okay.
Yeah. Okay. I think seems like a pretty good idea to me. Right. So how does this work? So I hope this construction makes sense. We're just gonna see whether it works or not in the next couple of slides. Well, okay, spoiler, it doesn't work. Why doesn't it work? There are a few problems, and they come in different levels of severity. The first problem is that making this work actually requires that the classical information processing happen at a speed which diverges as in the code distance. Really, it's the square of the code distance. That may or may not be a problem experimentally, but as a theorist, I don't want anything to diverge in the thermodynamic limit. So this is going to be a problem for us. The reason why this happens is actually very simple. It's just comes from self-interaction that how an anyon interacts with its own field. So an anyon here, it generates a gravitational potential like this, and it'll say be attracted to another anyon over here, and it'll move to get closer to that anyon. But after it moves to get closer to that anyon, we end up in this situation where it actually just sees the field that it left behind and gets attracted to its previous position. So there's this like self-interaction effect. In order for this to be eliminated, the field has to relax to very high precision so that this anyon doesn't see its own field. Okay, so you have to do a lot of relaxation of the field in between each anyon motion, and that leads to a diverging classical processing speed. Okay. Hope that makes sense. The other problem here is that actually, so there was only numerical evidence was given for a threshold, and we'll see that sometimes the numerics can be rather misleading. Okay, so what we're going to talk about today is an improvement of this idea. We're going to get rid of this. Oh yeah, please.
So it sounded like those were 2 reasons indicating that maybe at least this approach is challenging and it might not work.
Yeah.
I didn't quite get the impression for the specifics of the 2 reasons that the approach definitely doesn't work.
Right. So I'm gonna tell you that you can fix it. Does that make sense? So the gravitational attraction idea, I think, is a great idea. It's very simple. And the existing strategy for doing gravitational attraction using the scheme just described does not work. But we'll give a pretty lightweight fix.
Okay, it just sounds like you said something like this isn't necessarily a problem for experiments.
Oh,
More of a theoretical issue.
yeah.
And since there was numerical evidence, and I didn't hear that, kind of the threshold issue was kind of proved analytically really to be a problem, but it seemed kind of like there was a middle ground.
Yeah, I think if you just care about doing error correction in a 21 by 21 surface code patch, then you don't care if there's a threshold. You might not care about the diverging communication speed, depending on the exact context, your exact hardware. You may, though. What we're going to do in this talk is we're going to fix the theoretical issues. So we will give a construction that has a provable threshold, and we will give a construction with constant communication speed. And our construction will actually also be more useful. So it'll have better performance. I would be happy if it had worse performance, but solve the theoretical issues, but we'll actually get better practical as well. Okay, yeah, so that was kind of a summary. For people who are familiar with window decoding, kind of keep in the back of your mind that what we're going to be doing is like a streaming version of window decoding. I think that will give you some pretty good intuition for how this works. Okay. And then, yes.
You have a
tiny windows. Yes, think about, yeah, for you, think about streaming tiny windows in the rest of the talk. Yeah. Okay, 2 confessions, however. The first confession is that I'm going to be assuming throughout the talk that the classical processors are not subject to noise. A big motivation of the work with Shakar and Margarita was to drop that assumption, but here I'm gonna be using this assumption for the entire talk, and it's going to make life a lot easier. So only the qubits are subject to noise, not the classical bits. And the second confession is that I'm going to allow the number of classical bits used for each qubit to scale with the system size as a polylog of L. This is the number of classical bits per qubit that I need to get the optimal suppression of the logical error rate. And then here are my comments about that. Okay, so here's kind of for people who have thought about this and you want to see a comparison. This is kind of a comparison of how what we're going to do fits in with the rest of the literature. I'm going to get back to this table at the end, and hopefully it'll make more sense at the end. Okay. So here's the construction. We're going to begin to explain how this construction works. I'm going to begin with a simpler problem of just getting rid of noise on an initial noisy state. Okay, so this is sometimes called code capacity scenario in the QI literature. And our assumptions are going to be that we have the ability to make perfect measurements and that the error correction process itself is not subject to noise. Okay, so this is what we want to do. We want to find, in our case, actually a local Lindbladian that does this. You take a logical state, you apply some noise channel, and you want to find a Lindbladian such that as long as this noise channel is not too strong, you can evolve the system for a relatively short time and clean up all the anyons without making a logical error. So that's the goal. Here's a simple non-local strategy that would work. This is not going to be a local Lindbladian, but we'll make it a local in a second. A very simple algorithm you could do is just take each anion and move it towards the anion that's closest to it. Right. So at each time step, just move the anions by one site towards the closest anion. Okay. That's not going to give you something like a minimal weight matching, but if the anyons are sparse enough, you would imagine that this should pair them all up and not cause a logical error with high probability. Right. Okay. So it's clear that should work. How do we make that local? It's not too bad. The details are a bit technical, but I think the intuition is very easy. What happens is that each anion sends out, you take the anion to send out messages using the processors that are around it. And the way in which this can be done, there are many different ways this could work out, but here's one particular way of doing it. You take the messages to store an integer value, and you take that integer value to get larger as the message propagates. Okay.
So I think that this is on a torus or that there are spatial boundaries.
It doesn't really matter. If you're worried about the surface code where anyons can end on the boundaries, then you would have the boundaries where anyons can end just act like anyons themselves. They would also send out messages. So this is the anyon broadcasts its location, and what happens is that if you as an anyon receive a message, a value n, from some particular direction, that indicates to you that there's another anyon about n lattice sites away in that direction, right? And then you just look at where did the smallest message came from, and you move in that direction.
So this is a way to avoid the cell potential interaction.
Exactly, that the information just goes away from you at light speed, and you never catch up to your own signal. Makes sense? Yes.
Should I think of these messages and these ones as values of classical bits in your classical processors?
Yeah, that's right. So this information is we just have each classical processor is just going to store one integer. Really, there'll be a couple of different integers, but it just stores a couple of different integers, and we assume that it stores that information reliably. Yeah.
Does it still the integers coming from?
Yes. So really, how it works, you'll see that. Yeah, really how it works is you have messages going in all four directions.
Yeah.
And so there are four different types of messages on each site, and you use that direction information to decide where to move.
Each direction. Why not? Cross diagonal. Wow.
Oh, so you could probably do that as well. I'll show you the exact scheme I used in a sec, but I'm sure you could probably come up with a different scheme that maybe has a little bit better performance, but many options. The general principle is just send out information at the speed of light away from you. And you're kind of doing like sonar, sort of. You're just sending out these waves and you just move in the direction of the closest perceived signal. So this is what it would look like, right? If I had a bunch of anyons in space, here the purple shading is representing the strength of the messages they receive. So you would, as an anyon, you'd look to see where is the strongest message coming from, and you'd move in that direction. Okay. So here's what it looks like. I'm going to show you just an animation of this dynamics to make it totally crystal clear. I'm starting here from a state which has just tons of anyons, so I just applied noise with probability half on each qubit. And we're just going to evolve it. You can see that the anyons are, some of them, they get confused for a little bit sometimes. They're moving towards an anyon that they shouldn't be pairing with, but once those annihilate, they kind of can correctly find partners and annihilate.
Do you have a bound on like the Perkins time or all that?
Yeah, so you'll go to a anyon free state in time L.
Linear.
Yeah. So yeah, these are, let's skip the details. So what can we say about this method of cleaning up anyons? Well, it uses at most log of L classical bits per qubit. We just need to store the value of an integer that runs from 0 to at most L, right? So that's log of L bits. As we said, it fixes this communication speed issue. And using the fact that Michael just asked about, you can prove that there's a threshold. So you can prove that as long as the noise strength of your initial state is small enough, then your chance of making a logical failure is scales in this way. Okay.
Did you take into account the speed of light? Never thought it'd be asked.
Of course, the classical communication speed is order 1. So this works in a universe where we can do communication and processing at the speed of light,
but not instantaneous.
Yeah, of course. Yeah, no, nothing is instantaneous in any of the talk. Yeah,
except for the noise is classical.
That's also not instantaneous. Yeah,
well, physically, yeah.
No, but not in this talk. It is, yeah. And actually, having instantaneous communication for this approach doesn't really help you that much, but yeah. So okay, now I hope that makes sense. What we're going to discuss now is what happens when we run this error correction process in real time. which is really what we care about. So we have noise that's happening in the system continuously, and we have measurement errors. And we need to stabilize quantum information in this context as well. So here's what we're just going to run the same animation again, except now noise is going to be occurring all the time. So this is just for fun. You're not supposed to take away a firm conclusion from this animation. It's just for fun. But you can see that it's a little bit, the frame rate is a little bit slow on the big screen, but you can see that the anyons work. So these bursts of messages that are being created, indicated by the color, are being created either when pairs of anyons are created by the noise and then annihilated in most cases, as you can see, or a measurement error, say, falsely sends out a burst of message. But you can see that there aren't any anyons that have kind of survived to be unpaired and hang out. So this may be encouraging.
Is this below threshold or above?
There's actually no threshold.
Oh,
Yes. So let's address that issue of whether it's above or below threshold. One thing you can do is just run numerics. I kind of made the classic mistake of doing the numerics before thinking about the physics. And you do this. This is for the one-dimensional repetition code, which is very similar to the two-dimensional surface code.
You said there's a code capacity threshold, but
There's a code capacity threshold.
there's
Yes.
no fault-tolerant threshold.
Yes.
Sorry.
But so this numeric, what this numerics is doing is this is the fault tolerance setting. I'm running the dynamics for time L, the code distance, and I'm looking at the logical failure rate as a function of physical failure rate. And this is the classic thing you do. You do this, and you do it for different system sizes. You look for a transition indicated by the point where the logical failure rate is independent of system size, scaling rate. And okay, so you make this plot. It looks great. Looks like there's a threshold around here. Okay. Okay, but actually, that's not the case. So you can prove that the approach we just discussed, as well as all of the models proposed in previous constructions, do not have thresholds. So there's no actual phase transition where the logical error rate goes to 0 at infinite system size. So for an actual error correcting phase, this would need to go to 0, but in fact goes to a system size independent constant.
so there's error models you have to assume, like you're assuming imperfect syndrome extraction.
Yeah,
So-
that actually is not a big deal. So this applies, I think I have a remark on this. Even when the measurements are perfect, you still run into this problem that there's no threshold. Yeah.
What's different from the code capacity setting that you're doing?
Yeah, what's different from the code capacity setting, you'll see what's different in a second, but basically what happens is that imagine you'll see it. Let me just explain with when I have the slides. Of course, if you have decoding which is instantaneous across like non-local in space, and you have perfect measurements, then code capacity and fault tolerance are the same thing, right? Because you just completely clean up the errors at every step, right? Here you don't. The decoding process is local, and even when you have perfect measurements, the transient noise actually can screw you up, and it does screw you up in this setting. But yeah, this will be explained right now, actually. So here's how we understand this result. It's actually extremely simple. So here's the proof. Consider our system with perfect measurements, but with noise of strength P. Now, what the noise is going to do is it will create anion pairs in the system, which are separated by a typical distance of this C as indicated on the screen. This is just distance between a Poisson process of density of rate P, right? So this is the correlation length. And now all we do is we consider what happens to an anion pair whose separation is larger than this typical distance. Okay, so suppose the noise were to create such an anion pair. Well, how would it get corrected under this dynamics? Well, this anion would basically move towards the anion closest to it. Same with the other one. But with high probability, the closest anion to this one will just be some random anion created by the noise because it's its separation is larger than correlation. So what happens is these two anyons in this pair will actually just diffuse. They'll just move in random directions. Right? And they'll be uncorrectable. So,
What's that, D?
oh, sorry, D is the spatial dimension. Yeah.
Okay.
Sorry, I should have said that. Right, so if you have like a Poisson process rate P, what's the distance between 2 points? It's like 1 over square root of P. Okay, so hopefully that makes sense. And the problem here is that, well, these large pairs of distance larger than the correlation length, they're created at a rate which doesn't depend on the distance of your code, right? So in particular, your logical failure rate is not going to depend on the code distance either. So this argument leads to a memory time, the time you can retain your information for, which scales in this way. So it's like it's exponential in 1 over p to a power. And when you repeat this analysis at finite system sizes, you see you get this scaling, which really does look like a threshold in numerics if you're not very careful. You have a memory time which is diverging exponentially in your system size up to some constant, which diverges as p goes to 0, and then you have a constant scaling like this independent of system size after that. So people who have thought about partially self-correcting memories is kind of similar to that. So you can go back in now and you can look at the numerics in these earlier papers and see that this is indeed what's happening. So sort of the numerics done by Harold et al. were a lot better than what I was able to do on my laptop, and they look like this. This is plotted for different system sizes, and you can see that the average survival time sort of stops getting better as you increase the system size. And as you go to lower error rates, you can go to larger system sizes before it stops getting better. And you can think, if you just look at this data, oh, that might be a finite size effect, and really there's a threshold, but no, there's no threshold. Okay, so that's one of the main points of this talk. How do we solve this problem? Well, in our construction, there's a pretty lightweight fix, actually. And that's what I'm going to describe in the rest of the talk. Okay. The basic idea is that we're going to add a small extra classical dimension to the system. So we're going to take the array of processors to actually live in 2 plus epsilon dimensions, basically. There's going to be a really thin slab of processors. We're going to use that extra dimension to renormalize the space-time noise and get a threshold. Okay. And basically what we want to do is, since the memory time we showed was scaling as 1 over square root of p, what we basically need to do is we need to renormalize p to something that's like 1 over L, and then we'll get a super polynomially long logical lifetime. Okay. So we want to just bring down the noise by some amount. Finally, to account for measurement errors, we're going to make the confining this attractive interactions occur not between anyons in space, but between defects in space-time. So I'm not sure if this is like everyone is going to instantly understand what I mean by this, but a defect is a difference in syndrome outcomes at 2 consecutive instances of time. It indicates where a error has happened in your error correction process. And in the presence of measurement errors, you can have, for example, anyons that are falsely, you can have anyons that suddenly appear out of the vacuum, and you need to do the confining interaction between defects in space-time instead of anyons in space.
You just say it's like the movie Tenet, where they do like a time of
I've never seen Tenet, so
go back in time to attack base and forward into the pincer in time.
Oh, okay. The Tenet decoder. Okay.
Well, I don't think you can go back in time, or maybe you.
We're going to go back in time here.
Look back in time.
We will kind of go back in time. Yeah. So this is where you should think. Okay, this is where remember the comment about the windowing thing. Okay. Yeah. So here, what the construction. I'm going to show another movie in a sec, which I think is going to make it more clear. But bear with me for the pictures for a couple slides. We have our quantum system on the bottom here. We have an array of processors, which I haven't drawn. And these array of processors extend into an extra dimension. And so you should think at each point of this this box, there's one classical processor. These classical processes are going to be used to store a space-time history of the anyons for a time which is about the depth of this slab. So, and at each time step, what's going to happen is that these errors are going to be generated down here on the quantum system where the noise is happening. And then they'll be moved up this this slab just by one site at each time step. Okay. So basically what we're doing is we're generating a space-time history of the errors and we're just feeding it in and moving them. Okay. Now,
saying that the classical processors record where the NENs are at each time.
really what they record is the classical processor at this location here will, okay, it's simplest to start down here. This classical processor will record a defect if the syndrome measurement that it's responsible for keeping track of flipped sign at that time step. And then it'll take that information and just pass it up. And so the processor here will store the value of whether or not there was a defect, like time t steps into the past, if it's at a height t in this architecture. Does that make sense? So we're just kind of loading the history in. So far, I haven't told you what we're going to do with this. Right now, we're just like maintaining a buffer of the history as we load it into this architecture. And then what we're going to do is we're actually going to do the same message passing dynamics, the attract interaction, except we're going to do it on these defects as they're generated. And we're going to have the attraction occur in this whole classical, like this whole slab. Okay. So as soon as an error is loaded into this architecture, it's going to be attracted towards whatever nearest error in space-time, basically, it happens to find itself next to. Okay. And then finally, if an error happens to survive to this extra to get to the top of this this architecture, it's just going to stick there and continue to be attracted to any other errors that also happen to get up and stick to this top surface. Okay. So let's just look at how this happens. Okay. So what is being illustrated in this animation is as follows. Here, what's going on down here is all the noise events that are happening in the system. Okay. So this is sort of a space-time history of the noise that's going to occur on the system. The system is up here. This is just like what noise is going to occur in the future. Okay. As the noise happens on the quantum system, well, these classical processors keep track of where the noise events are occurring, and they then just do this message passing thing we were looking at in this now classical buffer region up here. Okay. So for people who know about window decoding, it's kind of like you're doing window decoding, except normally what happens in window decoding is that you load a whole block of space-time syndrome information into your decoder, and then you pause, and then you do all your decoding in the block, and then you resume, right? So there's this procedure whereby you like pause and you assume the noise doesn't happen for a while and you do your decoding. Here you're kind of just doing error correction as soon as the defects are fed into your buffer. So this is why I'm referring to as a streaming version of decoding. What you can see is that hopefully from this animation, you can see that not too many errors survive to make it to the top of this buffer. In fact, the errors are getting less and less dense as you move up. So the small scale errors are being corrected as soon as they move in. And only those errors which have a separation which is comparable to this distance can actually survive to make it to the top surface. So you should think of basically this dimension here as being a renormalization group dimension. Only the large scale errors survive to make it to the top.
But couldn't they have more like a diagonal distance and still be like corrected and not make it to the top because you're correcting both in space and time?
Yeah, definitely. Yeah. So the exact, I think I have this on a following slide, but if you have some errors which are contained in a box, space-time box of size R, then they only make it to the top of this buffer if R is at least the size of the buffer. Okay. So what can we say about this construction? Well, the first thing we can do is prove the following result. As long as you take the depth of this buffer to be polylog of systems of the code distance, then there's a threshold. And below threshold, you get this scaling for the error rate. Okay. So yeah, some remarks about this. One remark that I find interesting is that if you're doing decoding locally, so you have this local processor architecture, I believe that no decoder of that form can ever have a equals 1 here. So if you're thinking about how you should be able to suppress logical errors, you would normally expect that you can below threshold, you would get a scaling like this to the code distance, right? Because you have to get an error bigger than the code distance when doing optimal decoding to cause a failure. But if you're doing decoding locally, you can have these like gerrymandering events where a small number of errors relative to the code distance can create an adversarial like failing of how the decoder operates. And so you actually do pay an asymptotic scaling cost for doing decoding locally. So one can prove that in the decoder that we're talking about right now, but I believe it's a statement that holds in general. Yes.
Does this A depend on Z?
The A does not depend on Z. The A is like log base A of B, where A and B are some numbers of order 1. I think for the construction we're talking about, A is like 0.9. Yeah. This remark doesn't really matter for practicalities, but I still find it interesting.
Maybe you thought of this, but does the properties of the critical point change when you do this, or is it just about some threshold?
When I do the
When you add this like extra, because you already had a threshold in the previous decoder, it just didn't go to 0 failure probability. But
I don't think there's a really threshold in the previous.
You had a phase transition where you went to constant failure probability, and then at threshold you always have constant failure probability. I'm just wondering if the threshold.
But sorry, the previous. What do you mean by the previous thing? Had a phase transition? I don't think I had a phase transition there. I don't think there's anything sharp in the thermodynamic one.
No, there should be. We can talk about.
Okay. Yeah. To me, it's like a
you always see phase transitions like that all the time, where you go to finite failure probability.
Okay. Yeah, let's talk
You
about
can
that. Sounds cool.
Think of it like it can still be distillation, so it's still like a relevant phase transition. But
okay, let's debate this afterwards. Here I don't really understand much about the critical point. I'll show you a little bit of numerics, but I don't have a lot of understanding. Yeah, another remark is that if you just want a phase transition in this, I guess you said there was a phase transition already. But if you want a phase transition at which the memory time goes to infinity after a point, then you only really need log of L depth. So for people who are familiar with window coding, this is like exponentially better than what you would get there, where you need to take a window the size of the code distance. Okay. So hence it's much more lightweight. We're trying to make something like yeah, and although I haven't described it and the animation did not show it, this whole construction works in basically works in continuous time. If you want to know what basically means, we can talk about it later. Yeah, so I have some slides sketching the proof of this. I think I might not go into a lot of detail because the methods aren't super interesting. They're not super novel. It's kind of just turning a crank. But I'll just give you a sketch so you can be convinced of the argument. It's a standard kind of clustering analysis originally due to Gatch that has been used by Jim and many other people since then in doing decoding. And it basically operates in the following way. I'll just kind of describe it in words. You show that if you have a cluster of noise events, which are well isolated from other noise events and are contained in some box of a certain size, you show that this, maybe I'll just flip ahead to some side. What you show is that if you have a well isolated box like this, and if this distance is smaller than the size of your buffer, then these anyons will just get paired amongst themselves by the decoding dynamics. So the decoding dynamics will apply some correction that pairs up all of these without pairing them to any anyon outside of the box. And then you show that this happens as long as this box size is smaller than the depth of this buffer. So what this means is that the only errors that actually reach the top of your buffer are those that came from a cluster of anyons whose size is bigger than the buffer size. Right? Okay. So what that means is basically that the top of this buffer is experiencing a renormalized error model, right? Where you only get where basically the noise rate is reduced by this factor, right? So this is how it works. The only things that survive to the top are those that came from a box of size Z. Z is the depth of this buffer. And therefore you get this kind of a renormalized error rate. This follows because in the way we're defining things, a box of size Z has to contain at least some number of noise events that scales with Z. So you get an exponential suppression in your effective error rate as a function of how deep the buffer is. Then by the earlier argument we gave where we said that T memory was like the exponential of 1 over P, you just replace P with the renormalized error rate. And so since we're exponential in the renormalized error rate, you just take taking Z to be a polylog of the system size is good enough to get the best error suppression that you can get. Okay. So renormalize a bit and then use our old argument. So let's just confirm that in numerics. Now we can do numerics confident that there is a sharp threshold. And for the scheme that I described today, this is what you get. So in particular, for the surface code with equal strength measurement errors and depolarizing noise, you get a threshold around 1.5%. So that's there's still room for improvement. Minimal weight perfect matching is like 2.9%. But it's way better than any other local thing so far. And since I didn't put any effort into trying to make this number large, I think there's some room for improvement. And this is in the regime where things can actually be useful, especially when you look at the actual values of these numbers as a function of P. Okay. What's shown in the inset here is just the gamma is like the fit of this sub-threshold behavior for P to the gamma. And you can see that gamma basically scales like L. So I had this fact about gerrymandering earlier, but it doesn't really enter into the practicalities of this.
So you said this, can you say more about the error model?
This is the standard phenomenological error model. So IID noise of strength P on every qubit and IID measurement errors.
So you're making measurements and you assume this error rate. You don't like take the circuit level noise or something. No,
so just because okay, really the only thing that's relevant is how does this number compare to minimal weight perfect matching in the same errors?
Well, that's how you're thinking about it. I see.
Yeah, so if you want to do circuit level noise, probably divide this by 3 years.
Well, that's maybe.
Yeah, why not, right? What?
But it's within a factor 2 with the same error model of what global error processing would do.
Sure, no, I get it.
Yeah.
I get the statement. Like the result is clear.
But
Yes.
it would still be exactly a factor 2 for under.
Yeah, I don't know.
Circuit level, maybe not
Different
full, but
I think so, but the circuit level noise it's like some details about the exact.
Sorry, I was just confused about the error model.
Yeah, I didn't write it on the screen, so you're forgiven. Yeah, okay. And then the one brief comment you were asking about the phase transitions. This is something that I find interesting from a condensed matter perspective. So you can look at the nature of the phase transition that occurs. Here I'm just showing you what happens in 1 dimension. I think the one-dimensional repetition, the transition in the one-dimensional repetition code is more interesting because phase transitions normally don't happen in 1 dimension, at least not in equilibrium. So one can run numerics on this transition in 1 dimension, extract some universal features of the transition, and you get some continuous transition that I don't, I've never encountered before. I think it would be interesting to understand exactly what's happening here, but fortunately don't have any understanding.
But
At
what,
the
why
moment.
did you take rational? Why do you expect rational?
Squiggles everywhere, sorry, it's not equal.
But why do you expect rational?
You don't, sorry, this is just, okay, this.
You don't like writing numbers.
I don't write, yeah, well, okay, this slide is supposed to be like, look at this interesting thing, I haven't thought about it very much.
No, I
It
get it.
would be very cool to look at in the future, so I don't know what these numbers exactly are.
It's like 1.50.
Yeah, probably not that good, but 1.51 or something. I chose rational numbers that obey hyperscaling. Hyperscaling is indeed satisfied for as far as I can tell. It's satisfied with d equals.
Right, there's probably a upper critic, like this, you can just have this Anion model in any dimension.
That's right, yeah.
So there's some upper critical dimension.
Presumably, I haven't done the numeric. This is the only thing I have done.
Oh, but
Here it's
Yeah,
here it's very simple. You have a magnetization. It's the repetition code. So you have a local order parameter. I'm curious what kind of like field theory would describe this process. I haven't seen these exponents anywhere, but
but you would, sorry, what's just, I'll let you go on.
yeah, this is just supposed to be a provocation, not like I don't have a lot of stuff behind this.
Provoke.
What's the sync in these?
Yeah, so okay, I need to be a bit better about my slide. So there are two ways of doing the dynamics. One is synchronous, where you have a discrete time dynamics and all of the processors update in unison at every time step. Asynchronous dynamics is what would happen if you had a Lindbladian and the jump operators, so the executions of the processors are just happening randomly according to independent Poisson clocks. And the two methods of doing the dynamics are distinct universality classes of transition. This is kind of a generic fact that synchronicity changes the universal properties of critical phenomena, but it's something that no one understands. Okay, that's basically all I wanted to talk about. So I'm just gonna throw up a couple summary slides. So here was the table again. Just comparing different things. So minimal weight matching is what we currently use. And what we talked about today is on the far right. And so yeah, this is just a summary.
Can you go through everything?
Sure, okay. Yeah, every row. Okay, do we have a threshold?
Right.
By a threshold, I mean p logical going to 0 with large code distance below a. So let's give everything except this field-based gravitational interaction thing a check for that. Maybe I want to talk to maybe Jim about whether it should be a check or not, but
Sure.
yeah. Then and Cyrilson is the thing that I did with Shankar and Margarita, and it's a 3-dimensional version of that. Okay. So it's not in actually 2 dimensions. It's a whole stack of toric code. Local means nearest neighbor interactions between processors and finite communication speed. So minimal weight matching is not, you can't do that locally, like it's an X. The field-based, the gravitational interaction thing also gets an X because it had to have this like infinite communication speed. Right. Homogeneous means that the dynamics, basically means that the dynamics can be generated by a local Lindbladian. So we get an X for minimal weight matching for obvious reasons. We get an X for Harrington's decoder and our thing because these approaches rely crucially on synchronicity. So they only work when the dynamics is updated. You have this like reliable global clock that synchronizes everyone. So they get X and then our work. I didn't really talk about it, but it can be Lindbladianized.
There's no way, it has to be non-Markovian. Time. Block time.
No, yeah, that's okay. Each processor is getting updated according to an independent schedule. Right. It's like you have a classical Lindbladian in the bulk, some continuous time Markov process in the slab, and then there's like a quantum Lindbladian at the bottom. But you don't have to synchronize the processors together. So everything happens according to random Poisson clocks, and you still.
But this is homogeneous, okay, but then
Yeah.
it's homogeneous in like this 2 plus epsilon.
That's right.
Okay.
And we should talk later about the Lindbladian part because there's offline. Number of classical bits per qubit. So this is like the classical overhead of our approach. The thing that would motivate the work with Shankar and Margarita, this is this one. There are no classical bits anywhere. And so the thing with Margarita and Shankar is that since there are no classical bits anywhere, all of the information about where the syndrome should be moving and the space-time history and stuff actually gets encoded in the anyons in the quantum system. And that just makes that's why it performs so poorly, because you're encoding it in this very complicated way. But in the present work, we got away with using polylog to get the maximal suppression of the error rate. I'd like to reduce that number, but I don't know how to do that at the moment. This threshold, this means equal strength depolarizing noise and measurement failures to the numbers. And useful, you can make your own judgment. That's my judgment. Yes.
Question about the classical resources and how they're used. I can see how these local classical processors emit information so that the anyons know what they ought to be doing.
Right.
How do you say that the anyons do what they're supposed to do? Does that not require more classical control?
A tiny bit of classical control. So you need to what you need to do there is you need to look at the messages that you're getting, decide which message is the smallest. So that's some comparison between a couple integers. And then you need to say move the anion in this direction.
Yeah, and what does that step take?
That takes a constant number of bits of RAM.
Valley. But
Oh, you could apply a Pauli if you want. You could apply a feedback on the system if you wanted to. You don't have to. You can just like update your poly frame if you like instead. But the extra information is just comparing some integers and then sending a signal about where the feedback should be applied.
Yeah, so I understand about how these classical processors take care of the communication of information.
Yeah,
And identifying which direction to move in.
yeah.
The question was more about how physically you get the anion to move in the right direction.
Yeah, so you could just apply feedback to the system. So you could how that would work is the processor would say, hey, we need to move the anion over here, send a signal to do that, and then you would have a device which takes in that signal and applies like poly X on a particular qubit.
Are you imagining having that be a separate external control system or also
Autonomous, yeah. That decision is made locally, so each processor decides for themselves what they want to do.
So again, I totally follow you with on making follow you regarding making decisions.
Yeah,
It's the implementation of the decisions that I'm asking about.
yeah. Every processor implements their own decisions without consulting anyone else.
But they have to have the capability of, if you want to actively update, they have to have the capability of applying them.
They have to in the theory world, it's simplest to assume that each processor can apply any poly operator to the 4 qubits that it touches.
Okay.
And it does that without doing any like kind of democratic process. It just yeah, it does that. Yeah. Cool. So where do we want to go in the future? Well, here's some questions for theory. I'd like to reduce the classical overhead even further. So polylog is not bad, but could we do constant without running into all these problems with the hierarchical approaches? I'd like to, and then some more kind of condensed matter questions. How do we characterize the error correcting phase? What about the phase transitions? How do we think about this example as fitting into the larger, landscape of robust quantum phases of matter? For experiment, you can also ask like, okay, how should we optimize this construction to run on Google's device, for example? And can we, can this message passing approach be useful for quickly decoding other types of codes? There's actually a startup that's doing this, which I found kind of interesting. So if people know Yizhuang Yu and his friends, they have a startup called Eden Code, and their first thing is to use machine learning to find the best possible version of this construction I just discussed and run it. So yeah, if you want to play it, they made a demo of this. If you want to play around, you can go to their website. And that's all I wanted to say. Thanks for your attention.
You have some connection to this company, some financial stake.
Yeah, well, I have some equity, so I'm an advisor. But it's yeah, I'm really interested in like actually making this work, and it's cool to talk with people in the industry, but I still find it kind of surreal that you can just
But they're,
You can,
they're,
like,
they're trying to live exactly what you wrote for the paper about.
yes, that's right.
It was
Yeah.
like a month ago.
Yeah.
Okay. Almost 2 months ago.
Yes.
I guess what goes wrong if the classical computation is not noiseless?
Yeah, the biggest problem is that, so remember we had this, we're storing this little history buffer, right?
Yeah.
The biggest problem that you'd run into is a classical processor just forgets a defect or an anion at a particular location, right?
Cosmic ray flips bit in your mind.